Hello, welcome you all to the 8th session of for this NPTEL course titled Multirate-DSP. Myself, Sourasis Chatterjee, a PhD scholar from IIT Kanpur, and today we'll solve some numerical problems regarding the content of lectures from week 8. So, before diving into problems, let us first briefly revisit the concepts that have been taught in the lectures from week 8. So professor basically discussed, we have seen the main focus of the lectures have been capacity of wireless channels, you have also seen something called ergodic capacity, which is nothing but expected value of SNR. Of course, expected value comes into play when there is some randomness in wireless channel. Channel actually fundamental is random, which has been discussed in details in the lectures. Flat fading channel, let me write it down. Actually we'll see numerical problems based on each of those concepts, so I'm just kind of warming up to all this. Flat fading channel basically means your just consider your channel gain varies with time, such as for if one time instant it's amplifying your signal whatever being transmitted. Amplifying means your multiplying factor is greater than 1, then maybe at next instant it will attenuate your signal. That is that multiplicative factor is actually varying with time. That is what flat fading channel is. And next we'll see we have seen a very fundamental power allocation strategy in wireless communications, namely water filling algorithm, which is optimal power allocation strategy. This water filling algorithm concepts and derivation have been done in details in the lectures, but anyway we'll solve a problem regarding this water filling algorithm, where we will also somewhat elaborately revisit what are the concepts there. So it's like basically you in a very crude sense you assign more power to a channel which is strong in order to achieve a maximal rate. That is what the concept behind water filling algorithm is. And you don't assign any power to channel which are weaker based on certain conditions. So with all this in mind, let us move to our first problem. So these are the content of lecture from week 8. Okay. So in first problem, it's asked that we are asked to consider a AWGN channel with SNR 15 dB. What is the capacity of channel per bandwidth? So it gives me occasion to briefly tell you what AWGN channel is. Let me write it down for you. AWGN. This is AWGN noise basically arises from the at receiver end or at transmitter end from their hardware generated noise basically, and there are summation of so many different kind of noises. But that's not really on the scope of this session, so just briefly mention. Consider this system model X being transmitted to a channel again H, and here your noise getting added and you get Y, which is X plus N. So AWGN channel refers to channel model where you add a noise N, which is additive in nature. That is, it always adds up with the amplified or attenuated signal HX. Second thing is white. White part actually refers to the frequency response of noise is constant across all the frequencies. So what does it exactly mean? If you this N is in time domain, it's a noise. If you take a Fourier transform of that, which is denoted as NF, then the spectrum of NF looks something like this. It has a fixed this is axis F, so this has a constant frequency response across all the frequencies. So if you add the entire spectrum, the power of the noise comes out to be infinity theoretically, but fortunately your all the practical system operate in a particular bandwidth region. I mean, consider maybe this part only, like your receiver is working on this bandwidth only, minus B to plus B. So your only part of only noise that you should be concerned with is this part, the noise here. So if this is a spectrum value is N0 by 2, you should be concerned with the noise. Your noise power would be N0 by 2 times 2B, which is N0 B, because since the receiver hardware operate only on this bandwidth minus B to B, it filters out the rest of the noise power, because that is not exactly your concern. And Gaussian, you know, of course, because N is a complex symmetric Gaussian distributed, that's the reason. So with these things in mind, let us write down the SNR what we get from here. We get SNR as PS time HS square by N0 B. This is noise power. PS is transmit signal power, and norm of H square is nothing but, not if consider a scalar channel, so it's just reduced to absolute value. This is channel gain. Now channel gain is dimensionless quantity and transmit signal power is in watts, and N naught by B is also in watts because unit of N naught by 2 is basically a watt per hertz, so we multiply with B whose unit is hertz. So basically SNR is a dimensionless quantity. Let me explain again. PS has the dimension of watt, channel gain is a scalar, it's dimensionless, it's just a multiplicative factor, and N naught by B is again noise power, which is whose unit is again watt. Here N naught refers to PhD. Let me write it down. N naught is power spectral density, PSD of noise, unit is watt per hertz. When you multiply N naught times B, B is a unit of hertz, N naught times B become watt. So numerator denominator both units are watts, so therefore your SNR, which is the ratio between these two, comes out to a dimensionless quantity. And when we say that SNR is equal to 15 dB, dB is also dimensionless, no need to mention. What does we exactly mean? We mean that if SNR in linear scale, the value of SNR is capital gamma, therefore we obtain 10 times log base 10 capital gamma is equal to 15. So for computation of capacity of channel, we need the SNR, the linear SNR value of linear scale first. So how can we get that? You just take 10 to the other side, it comes out to be log base 10 capital gamma 15 over 10, which is 1.5. Therefore your gamma comes out to be 10 to the power 1.5. Let me check the value for it. Comes out to be 31.622. I'm rounding up to 3 decimal. And when it comes to the capacity of channel, let me write down the word capacity is very briefly. It is the maximum allowable rate at which data can be sent with arbitrarily low probability of error. So what does it mean intuitively? The channel capacity refers to the maximum allowable rate which you can use, at which rate you can transmit data through that channel with almost reliable communication. That is, the probability of failure of communication is arbitrarily low. But once you start transmitting data at a higher rate than the channel capacity, the channel no longer ensures the reliability of communication. That is, your probability of communication failure is going to be there. I mean, it's non-zero probability. That is the concept of capacity. And we have seen in lecture the theoretical capacity of AWGN channel. Capacity of AWGN channel C is given as B times the bandwidth of the channel 1 plus capital gamma log base 2 bits per second. Let me write it down for clarity that B is channel bandwidth by the way. You see some of the unit to be nats, so no need to worry. It's actually when you take the base of logarithm as e, that is your log base e, that is become our standard natural log ln 1 plus gamma. This become nats per second. The concept remains same, just the unit changes. Let me add a slide here. Okay. So we have seen that capacity in bits per second is given by this quantity B times log base 2 1 plus capital gamma. Therefore capacity per unit bandwidth, it also have a name also, that is called a spectral efficiency. This is given as log base 2 1 plus gamma, because it's obtained by dividing capacity by bandwidth, and its unit comes out to be bits per second per hertz. So for the problem in consideration, we have our gamma to be, what is the value? Let me check. Okay, 31.622. 31.622. Therefore our capacity per unit bandwidth, let us denote this by this quantity, capacity per unit bandwidth to be let us call it capital gamma dash. Capital gamma dash is equal to log base 2 1 plus 31.622 bits per second per hertz. So this comes out to be log base 2 32.622, whose value is, let me check on the calculator, comes out to be 5.028 bits per second per hertz. Let's check whether the answers are matching. The first one, okay, the first and second one have the unit in bits per second per hertz. They are not matching, but the other two are in nats. So by the way, we have seen that the difference between bits per second and nat per second, it's the base of logarithm changes. So we can write bits to nats journey consists of a multiplication of ln2. So this capital gamma dash is in bits. If we want to find its corresponding value in nats, it will come out to be ln2 whether you can see why I am using the multiplicative as ln2, because simply if you're consider your just a moment, suppose your x in bits is something like log base 2 some gamma, and x nats is log base e gamma. So if you divide both of them, x bits by x nats, it basically comes out to be the above one you can write as follows. From bits to nats transition, I just need to product with ln2. So let us check what this value comes out to be. 0.693 is the value of ln2. It's a well-known quantity, times 5.028 nats per second per hertz, and we obtain this as 3 to round up to 3.485 nats per sec per hertz. Let us check whether this matches. Okay, this one does. The third one is the correct answer. The capacity per unit bandwidth of the channel for this problem comes out to be 3.485 nats per second per hertz. Okay, with that we move to our next problem. Here also we consider a AWGN channel and bandwidth 40 megahertz. So let us write down the informations. Bandwidth B is equal to 40 megahertz. Received signal power 10 milliwatt. Received signal power 10 milliwatt. We denote it as PR. Also mention noise power, spectral density n0 by 2. we have seen already from previous example, but I am briefly drawing this for your understanding. This is nothing but the spectrum of Fourier transform of noise, AWGN noise, which actually extends from -infinity to infinity, but since the receiver operates only on finite bandwidth, the receiver hardware in particular, it cut offs anything beyond this operating band limited region. That is, your noise spectrum effectively becomes this n0 by 2. So from this you can see, from Parseval theorem we have seen in our week 7 discussion, that power in time domain is same as power from frequency domain only, and sometimes it's easy to compute one in one of the domain compared to another. So here from we get our noise power to be n0 by 2 times 2b, it's n0 by b watts, of course, and our SNR, which is a signal to noise ratio, signal to noise ratio, this comes out to be the ratio of received signal power PR by noise power n0 by b. And we have encountered this before. This is a dimensionless quantity, it's not necessary to mention. So let us write down the capacity expression. Basically the question asks what is the capacity we can achieve by tripling the received power. So instead of PR, if we are using 3 PR, what should be our received power? That's the question. So let us write down our present capacity of a AWGN channel. We have seen multiple times in lectures, and we'll see again and again till you have become very familiar with this. One plus capital gamma, this is capital gamma SNR, that means b log base 2 1 plus PR by n0 b bits per sec. So let us consider our present capacity. We denote it as CP, and it comes out to be, if you put the values in place, and also let us put CP dash is capacity which are asked in question, like CP is log 2 b times 1 plus PR n0 times b, whereas C dash p is bandwidth remains same, only your received power becomes triple, so it becomes 3 PR by n0 times b. So first we'll calculate CP, what is the capacity we obtain with PR given in the question. By the way, value of n0, let us write down something here, 2 into 10 to the power minus 9 watt per hertz. So this comes out to be CPU, B value is 40 times 10 to the power 6, this become log base 2, 1 plus PR is given as 10 milliwatt, so 10 into 10 to the power 3 if we are exact with our notion of watts here, and n0 is 2 times 10 to the power minus 9, and B comes out to be 40 into 10 to the power 6. Let us check. By the way, this unit is bits per second. Now 10 to the power 6 I am removing instead of that, I am writing it to be megabits per second. Megabits per second. And here we obtain log base 2 1 plus 10 to the power minus 2 by 8 into 10 to the power minus 2. Correct? Okay, correct only. So you get 40 times log base 2 1 plus 1 over 8 megabits per second. Now we see that when we consider CP dash, we can consider CP dash from CP only. You can see that only this term is dependent on received power, which now becomes 3 times. So CP dash is 40 log base 2 1 plus 3 times 1 by 8. If you compare both this expression, megabits per sec, it comes out to be 40 log base 2 1.375 megabits per second. Let me calculate the answer. Okay, it is coming out to be 18.37 if I round off to 2 decimal for the sake of exact matching with the answer. Mbps per sec, or you can write Mbp, megabit per second, that is the standard notation. Let me write here Mbps. So second one is the correct option. So with this we move on to our next question. So we consider a channel with free space path loss. What is the normalized capacity of channel? Normalized capacity means here the same thing discussed in first problem also, capacity per unit bandwidth, which is also called spectral efficiency, when transmitter and receiver are separated by a distance of 100 meter. Assume that transmit power to be 120 dB watt and noise power is 40 dB watt. And by the way, whenever we say dB watt, it just we must assume, you must know actually that it is sensitivity is a dimensionless ratio. So it always refers to some reference power, and here the carrier frequency is mentioned to be 900 megahertz. So free space path loss model Let us briefly discuss what that is. It assumes a line of sight path between transmitter and receiver. We call it transmitter without like with absence of any scattering in between. That is a transmitter and receiver are line of sight with each other, and there is no obstruction or blockage between them. And if their distance comes out to be d, and the antennas are isotropic, then actually the power received at receiver, which is denoted, let me write it down, PR is the received power, PT is transmitted power. So when an isotropic antenna transmits signals in 3D, what happens basically, the power is distributed on the surface of ever increasing sphere, and the sphere is actually the distance from transmitter to receiver, and that sphere gets bigger and bigger as the signal propagates in the space. That is the you can consider that larger the radius of sphere, the smaller the this your receiver's ability to capture power from a particular portion of the sphere. So your received power rapidly drops because of that, because by compared to when distance is 10 then compared to distance with 100, if you think intuitively, the earlier the entire power is concentrated uniformly on the surface of a sphere with radius 10. Now the same power has been concentrated with the concentrated on the surface of a radius with a radius 100 meter. So your effective power that you are going to capture become much more diluted for 100 meter case compared to 10 meter. So therefore your received power decreases proportionately. To model this uh, this practical phenomena, what is the free space path loss model says? It says that received power PR can be obtained by dividing PT transmit power over this quantity 4 pi d by lambda square. We'll discuss what this quantity is in a minute, but it's good to check that 4 pi d by lambda square comes out to be a ratio of PT by PR. So this part is again a dimensionless quantity. And if you replace lambda by the way, let us write down what these are. PT we have also mentioned transmit signal power, PR we have mentioned receive signal power, D as also mentioned this question is the distance between transmitter and receiver, lambda is wavelength of signal, but lambda is not mentioned in the question, of course, so you cannot use it directly. We can, on the other hand, you can use the property that lambda is equal to c by f, where c is the speed of light in free space, which is computed at 3 into 10 to the power 8 meter per second, and f is the carrier frequency Therefore, if you replace the expression of lambda here by this, it comes out to be this: pt times 4 pi df by c square. Now there is one thing, here your transmit power is not given as watt, it is given as 120 dB watt. So what does that mean? It means that PR is not equal to 120 because its unit is given in dB watt. Therefore it is using some other power as a reference. What does this mean? That 10 log base 10 PR is actually 120. Similarly, therefore we take logarithm, like convert this to unit on both sides as dB, because to find normalized capacity of channel we first know the PR. PR is the received signal power, that we need to know, and since PT is given in terms of dB watt, it's convenient to find PR also in dB watt. We can later transform it. So what the equation 1 we have, PR is equal to PT divided by 4 pi df over c square. We convert both the quantity on left and right. Take 10 log 10 on both sides, effectively converting the quantity into their dB watt equivalent. That is our goal. 10 log 10 PR, 10 log base 10 PT, minus, because since 4 pi df by c square is in denominator, we obtain 10 log base 10 4 pi df by c square. You can further simplify that: 10 log base 10 pt minus 20 log base 10 4 pi df by c. This side you have 10 log base 10 PR. So this term here is our received signal power in the unit of dB watt, transmit signal power in dB watt. This is this term, which is the main focus of the free space path loss model. This is the free space dB equivalent of free space path loss. Since this is a dimensionless quantity, it fits with the dB. It has no unit, by the way, it's only dB only. Therefore, if we put this, let us add some slide here. So this 10 log base 10 PR, we can also write in this format also, PR in dB watt. Similarly, 10 log base 10 PT, we can write it as PT dB watt, and this term we write as it is, that is 20 log base 10 4 pi dF by C. So this one is given to be 120, and this one we need to calculate. For that we need to know D, F and C values. The D is given in question to be 100 meter, F carrier frequency is also given as 900 megahertz, I guess. Let me check once. Yes, correct. And C, of course, we have mentioned 3 into 10 to the power 8 meter per second. So let us put all these values in place. What you will obtain here, 10 to the power 8 3 PR in dB watt is 1200 pi. Let me calculate its value using calculator. The value comes out to be, after rounding up to 2 decibel, 71.53. 120 minus 70, 71 minus 53, which results into 48.47 dB watt. So we obtain our received power PR as 48.47 dB watt. Now if we remember, we are given our noise power in 40 dB watt. So if you remember the SNR expression from the lecture, it is nothing but PR times PN. And PR is your received power and PN is noise power. Now if you take 10 log base 10 on both side again, So you get 10 log base 10 SNR equal to 10 log base 10 SNR, sorry, PR 10 log base 10 PR minus 10 log base 10 PN. Now this is nothing but PR dB watt, and this is nothing but noise power in dB watt. Now, PR dB watt comes out to 48.47, noise dB watt is given as 40, we get 8.47 dB, which is the SNR in dB expression. So SNR in dB scale is equal to 8.47. Now if SNR in linear scale is denoted as capital gamma, sorry, it's not capital gamma, not F, capital gamma, then you have 10 log base 10 capital gamma is equal to 8.47. From this you get your capital gamma is 10 to the power 0.847. This you obtain as, let me calculate, it comes out to be 7.036, and this is the value of SNR in linear scale. Now we are going to use this SNR to calculate the normalized channel capacity. Normalized channel capacity, that is nothing but capacity per unit bandwidth, which you can write as B times log base 2 1 plus capital gamma log base 2 1 plus capital gamma over B, which comes out to be log base 2 1 plus gamma, which is log base 2 1 plus 7.036 log base 2 8.036, and this comes out to be up to 2 decimal 3 bits per seconds per hertz. Let us check whether the options is up to 4 5 decimals or saying okay up to 2 decimal, then this fourth option is the correct one. Okay, with this we move to our fourth question. Here we consider a flat fading channel with instantaneous SNR given by small gamma as alpha squared times capital gamma, where capital gamma value is fixed to be 40 dB and dB scale, and alpha is the instantaneous fading coefficient that varies with time, and the bandwidth is given to be 20 kilohertz. Therefore, the probability distribution of alpha, which is the time varying coefficient, is given as follows. P alpha of 0.25. Okay, first let us start with the why instantaneous comes into place, because flat fading, any fading channel refers to, write it down, fading refers to randomness in channel gain. This is the important point to understand. Randomness in channel gain. That is, you have input signal X which you are feeding to this channel, maybe you consider channel to be alpha, and you are receiving a Y here. Of course, in AWGN channel you have noise here, so you have Y to be alpha X plus N. Then your alpha, this one, varies with time. Consider two extreme situation there. If alpha value is greater than 1, you can see you received a amplified or higher scale version of X transmitted signal, and sometimes alpha will have a very low value, that is less than 1. That means you will get a attenuated version of signal, and based on this, since alpha varies with time, this alpha X become random, which in turns make Y to be random. Therefore, the SNR of Y, based on Y, what we get comes out to be alpha squared times capital gamma, where capital gamma is equal to transmit power of input signal X over noise. But your SNR of Y, this is become actually instantaneous. SNR. Why we are calling it instantaneous? Because you see alpha varies with time, so this induces randomness in the received Y. Y now not only depend on X but also depends on alpha, which varies with time. Therefore, at any time instant, the SNR you obtain from Y, expression of Y, that is dependent on alpha. So as alpha varies, the SNR of Y at different time instant keeps varying. So therefore, the SNR is not fixed across time instant. You can see it as a case of temporal randomness, that is, it becomes random in time. That's where the instantaneous SNR concept has been introduced. Instantaneous SNR refers to SNR at a particular time instant, which is different from average SNR, which is what you get by performing expectation of this instantaneous SNR. It means basically you take SNR across all the time instants, or of course a large enough time instants, and you take the average value of them, you get average SNR. But instantaneous SNRs at every time instant keep differing from each other. So with that concept of mind, let us start with Let us solve the question. Here you can see your gamma value is capital gamma is given in dB term, 40 dB, which by now you can say in gamma gamma in linear scale. How do you obtain that? We have already seen it's like 10 log base 10 capital gamma is equal to 40. From here we get gamma to be 10 to the power 4, correct? So it comes out to be 10 to the power 4. Since this is SNR, it is a dimensionless quantity. Anyway, our bandwidth we have chosen to be 20 kilohertz. Now we consider the case when let us examine the probability distribution of alpha. Now what does it mean by P alpha of 0.25 being 0.125? This means with 25% probability, or from another point of view, once out of 4 time instant time varying coefficient alpha takes value of 0. Oh, sorry, I'm writing it wrong. Sorry. Probability is actually 0.125. 0.125 actually is 1 by 8. So there is a with 12.5% probability, or every once out of 8th time instant. It should be 8 time instant alpha takes value of 0.25. Similarly, what does P alpha of 1.25 being 0.125 means? This also means with 12 let us write down a little bit easier to understand language. Every 1 out of 8 time instants alpha takes value 1.25. Now when you sum up all these alphas, p alpha of alpha i's over all I, that is p alpha of 0.25 plus p alpha of 0.5 plus p alpha of 1 plus p alpha of 1.25. You sum all these probabilities up to check whether it's a valid probability distribution or not. Once we are confirmed this is a valid probability distribution, we will proceed to compute the average SNR. And you can see this comes out to be 1, so it's a valid probability distribution. Now how do we find average SNR? So it's basically in practice alpha is a time varying coefficient which can take as many values as possible, but here alpha, the probability distribution is given to be discrete. That means alpha can take one of these 4 values, that is 0.25, 0.51 or 1.25. so therefore there are 4 instantaneous SNR possible. So our job is to compute the average SNR, which is nothing but we need to compute the instantaneous SNR for all these 4 different alpha values, and we assign these probabilities as their weights, and this weighted average of the instantaneous SNR is our average SNR. The reasoning behind is like this, that if p alpha takes value 0.25 with a probability of 0.125, the corresponding instantaneous SNR correspond to alpha is equal to 0.25 also happens with probability 0.125. With this, let us proceed to calculate the average SNR. First let us add a new slide here. Okay, so first we'll consider instantaneous SNR corresponding to alpha is equal to 0.25. By the way, write different alpha values in series of ways, that is alpha 1 is 0.25, alpha 2 is 0.5, alpha 3 is 1, and alpha 4 is 1.25. Now corresponding instantaneous SNR, small gamma 1, this corresponds to gamma 2, this corresponds to gamma 3, this corresponds to gamma 4. So when we say we are computing gamma 1, we are basically doing alpha 1 square times capital gamma is 10 to the power 4. Therefore this is 0.25 whole square times 10 to the power 4. This comes out to be 0.0625 into 10 to the power 4. This is 625. Now we proceed to compute gamma 2, which is alpha 2 square capital gamma. Alpha 2 is given as 0.5 input square times 10 to the power 4 at 0.25 into 10 to the power 4. This is 2500. Gamma 3 we obtain as alpha 3 square capital gamma, that is 1 square times 10 to the power 4, which is 10,000, and and we have gamma 4 to be alpha 4 square, is capital gamma, is 1.25 square into 10 to the power 4. Is it 1.25? Yeah, correct only. Just a minute here, I guess. So this should be 1.5. I put the question as the wrong one. This should be 1.5. Okay, alpha value is 1.25 is not, it should be 1.5. Okay, with that we need to make change here also. We obtain 1.5 whole square times 10 to the power 4. 1.5 square comes out to be 2.25 for 4, which is 22,500. So these are the 4 instantaneous SNR values. Let me write it down. Gamma 1 625, gamma 2, it's the lowest value of SNR, gamma 2 2500, gamma 3 10,000, and gamma 4 22,500. Okay, now average SNR is weighted. Average SNR is nothing but weighted average of instantaneous. By the way, since this corresponds to alpha 1 value, this corresponds to gamma 1, so probability of small p, probability should be denoted in small p. Probability of gamma 1 is same as probability of alpha 1, which is 0.125. Probability of gamma 2 is same as probability of alpha 2, which is same as, is given as 0.25. Probability of gamma 3 is same as probability of alpha 3, which is 0.5, and probability of gamma 4 is same as probability of alpha 4, which is 0.125. Now average SNR is obtained at weightage average of instantaneous SNR, where the weights are corresponding probability values. That is, if you call average SNR, you denote it as gamma average. It is nothing but gamma instantaneous with probability of gamma I over I, all i's. Here I refers to 4 cases. This is, let us calculate then. It is 625 into 0.125 plus 2500 into 0.25 plus 10,000 into 0.5 plus 22,500 into 0.125. Let me calculate the value here. $625 times 0.125 plus 2,500 times 0.25 plus 10,000 times 0.5 plus 22,500 times 0.125. It comes out to be 8515.625. This is the value of average SNR in linear scale. Does the answers are in linear scale also? No, it's in dB scale. So let me gamma average in dB scale, as we already familiar with how to write this. 10 log base 10 8515.625. Let me calculate it. Log base 10 8515.625 times 10. Okay, it comes out to be 39.3 decibel. Let us check which of the answer matches with our computed answer. So it's 39.3. Third option is the correct one. We now move to the fifth question. Fifth question Okay, one particular data is missing for the question in fifth and onwards. It's a single tap channel with bandwidth. This information was missing, sorry about that. 30 kilohertz. So this is a single tap channel with bandwidth 30 kilohertz. In previous question you are given alpha 1s, that is time varying channel coefficients. Here the problem seems a little bit easier. Here you are given instantaneous values of SNR itself, that is the gamma 1 is a instant, let me write it down properly. Gamma 1, gamma 2, gamma 3 are instantaneous SNRs. You can say that gamma 1 value is 0.4, gamma 2 is 6, so gamma 3 is 12. Therefore gamma 1 corresponds to worst channel conditions, and gamma 3 corresponds to best channel condition. Instantaneous SNR gamma 1 value of 0.04 is observed with probability P of gamma 0.4 as 0.25. Similarly, instantaneous SNR of gamma 2 value of 6 is observed with probability P of gamma 6 is equal to 0.35. Instantaneous SNR value of gamma 3 of 12 is observed with probability P of gamma 12 to be 0.4. Let us check whether the probability distribution are valid or not just by summing up all probabilities of instantaneous SNR over I, that to be 0.25 plus 0.35 plus 0.4 comes out to be 1. This is fine then. Now ergodic capacity of channel is nothing but the instantaneous capacities times their probability. The concept is similar to average SNR only, just instead of average SNR it's average rate. It's like weighted average of instantaneous rate. When the rates are weighted according to their probability of occurrence. Let us write down ergodic capacity of channel C ergodic is given as summation over all instantaneous rates. Rates are given for AWGN channel as follows: B log base 2 1 plus instantaneous SNR, and this is multiplied with corresponding probability of occurrence of instantaneous SNRs. So B part is common, you can safely take it common. It leaves only summation over all instantaneous SNR weighted by their corresponding probabilities. So they come out to be log base 2 1 plus 0.4. This is multiplied with probability 0.25 plus log base 2 1 plus 6 multiplied with probability of 0.35 plus log base 2 1 plus 12 with probability of 0.4. Let me calculate the values. Log of 1.4 by ln2 times 0.25 plus ln7 by ln2 times 0.35 plus ln13 by ln2 times 0.4 whole multiplied with 30. It comes out to be 77.523 up to third decimal. Okay, the answer is in fourth decimal, so you include the fourth decimal number also. kbps. So let us see which of the option matches. It's option C, 77.5232 kbps. With that, we move to our sixth question. Okay, the sixth question fetches its data from question 5 only. So the probability of instantaneous SNRs, 3 different instantaneous SNRs are given. They hold same and their corresponding values, of course, the instantaneous SNR values and their corresponding probability values hold similar for question 6. Now question 6 looks for the capacity of channel when CSIT is not available. It asks to consider all possible outage scenario and for each one use the corresponding transmit scheme. Okay. By the way, CSIT refers to channel state information that is available at transmitter, and CSIR refers to channel state information available at receiver. Now you think what is going to happen when transmitter doesn't have the channel state information. CSIR, like consider the case when transmitter is not having the channel state knowledge, but it has to transmit data as a particular SNR, correct? Now if that instant the channel capacity, instantaneous channel capacity, which is characterized by instantaneous SNR at receiver at that time, comes out to be A, and transmitter sends at a rate B which is greater than A, then according to channel capacity theorem, what will happen? There is a possibility of communication failure because your instantaneous channel capacity is A and you are transmitting at a rate B which is greater than A. So effectively your transmitter is transmitting at a higher rate than the channel capacity at that time instant, and it is doing that because it is unaware of the channel state information. It do not have the information, so it cannot calculate the channel capacity. Therefore communication failure, there is a possibility, and this communication failure is denoted as outage, and probability of this communication failure is denoted as probability of outage. So let me outline the case here for understanding. Suppose at any time instant channel capacity is C1 and transmitter which is unaware of channel state information transmits at a rate C2 where C2 greater than C1, then probability of communication failure is non-zero, which is also termed as probability of outage. This is the concept of outage, correct? Okay, first we consider the instantaneous capacities. Instantaneous capacity C1 corresponding to gamma 1 is C1 is equal to B times log 1 plus gamma 1, that is 30 times log 1 plus 0.4 base 2, of course, 14.563 up to 3 decimal kbps. Similarly, instantaneous capacity C2 corresponding to gamma 2 is, okay, let us not for confusing with this, let us call C dash and C dash here, C dash 2, C dash 1. Just don't confuse this. These are regarding this problem only, and these are only the theoretical insight. This is Theo. Let me mention it properly. This is theoretical inside, and this C2 we obtain as B times log base 2 1 plus gamma 2, that is 30 times log base 2 1 plus 6. This comes out to be 84.22 kbps. And instantaneous capacity C3 corresponding to gamma 3 is C3 is equal to B log base 2 1 plus gamma 3, that is 30 times log base 2 1 plus 13, 1 plus 12, 3 value is 12, and it comes out to be 111.01 kbps. Now we have to consider three separate cases since there are three instantaneous capacities. If we have two probability of outage to be 0, that is, what does probability of outage is 0 means? That is, we need to have probability of communication failure to be 0. That is, we cannot tolerate any communication failure. So how do we ensure that? We must look for, there are only three values of instantaneous capacities, correct? 14.56, 84.22, 111 point, correct? Which one corresponds to the worst case? The worst case instantaneous capacity corresponds to 14.56 kbps. So if I want to ensure that there is no communication failure, what does the channel says? The channel SNR doesn't go beyond 14.56. So if my transmitter sends data at a rate less than or equal to 14.56 at all instants of time, then what I am doing, I am avoiding any communication failure, because I know that channel capacity doesn't go below 14.56. So if the transmitter transmit at this rate or below that all the time, it is going to achieve probability of outage to be 0. Therefore write me down the case which is denoted as case 1. If we want probability of outage to be 0, transmitter must always send data at or below maximum, not maximum, at or below worst instantaneous channel capacity, which is in our case C1 is equal to 14.563 kbps. Let me add a slide here. So what do we have as of now? So to ensure the probability of outage to be 0, we must transmit always below this rate, below or equal to this rate, this capacity. Therefore the corresponding throughput that we are able to achieve for this condition and probability of outage is 0, which we denote as R1, is as given in lecture. You can see the 1 minus probability of outage times C1, and this is probability of outage 0, so it comes down to C1 only, 14.563 kbps. Correct. Next we move to case 2. We say that we can tolerate, we are agreeing to have a probability of communication failure which corresponds to the probability of worst instantaneous capacity, that is P of gamma 1 to be 0.25. So we are saying we are agreeing to tolerate 0.25 or 25% probability of outage. That is, every 1 out of 4th time instant my communication channel will go to fade. We can tolerate that. So it's considered the probability of max outage that we can tolerate is 0.25. Therefore, what should be our choice of channel capacity? It's of course the next best, which is gamma 2 in our case. Correct. So if we are willing to tolerate probability of outage which is equal to the probability of worst case instantaneous channel capacity, we can look for next best channel capacity scenario, which is 84.22, that is C2. Correct. This another point of view of seeing this is we allow only gamma 1 to go in outage. So if we ensure the rate, like transmitter is always going to send at a rate equal to or below this C2, which is 84.22, what is going to happen? Because channel with probability 0.25 or 25% of time, it will experience a SNR of 14, and then communication failure will happen because you are transmitting at or below 84.22, which is above than 14. But you say that I am okay with that, I will tolerate probability of outage of 0.25. At this cost, we are able to transmit at or below rate of 84 all the time. Correct. So what is the throughput we obtain? Average throughput, you obtain 84.5 84.22 kbps, but that is also will be successful for 1 minus 0.25, that is 0.75 or 75% of time that would be successful. So the throughput from this case 2 you can ensure is given as 1 minus probability of outage times C2. Correct. That is 1 minus 0.25 times 84.22, which comes out to be 63.165 kbps. Correct. Now you are saying I am not satisfied with that, I am willing to trade off more probability of outage, that is I can tolerate probability of outage which is equal to probability of gamma 1 and gamma 2, which corresponds to probability of C1 and C2, that is 0.25 plus 0.35, that is 0.6. that is we are allowing gamma 1 and gamma 2 to go into outage, because 60% of time channel capacity is either gamma C1 and C2. We are willing to transmit at or below C3, which is higher than them. So we risk the probability of communication failure for 60% of time, but in exchange we are trying to achieve higher rate. So let us see what is our throughput is going to be for this third case. Because now the transmitter can send below or equal to C3, but that will be successful only 1 minus P outage, that is 1 minus 0.6, 40% of time only. So is the throughput, average throughput is really higher? So let us check. 1 minus 0.6 times 111.01, correct, kbps. It comes out to be 44.4 kbps. Now denote R2 here. This case we denote as R3. Previous one I think we denote R1. Correct. Okay. Now the capacity of channel, because channel is we are interested only in average throughput that can be reliably transmitted, the rate at which data can be reliably transmitted, which is the capacity of the channel without CSIT, and this is given as that the second case is the optimal trade-off is happening. If first case we are making our transmitter rate probability of outage 0, that's very good. From probability outage there is no communication failure, but also we are getting a very low rate because we are transmitting at watts channel capacity. In the second case we somewhat trade off the probability of outage. We are say okay, 25% of time we allowed communication failure. In return I want to transmit at a higher rate all the time, and average throughput comes out to be 63 in that case. For the third case we say that we will trade off more probability of outage, that is we can allow 60% of communication failure, but we are willing to transmit as the highest channel capacity. But it turns out, since your probability of outage is significantly high, your average throughput over which you can the data rate at which you can reliably transmit over the time comes out to be less than second case, because although your instantaneous capacity will be high, but it will be only high for 40% of time. 60% of time there is a chance of communication failure. Therefore capacity of channel without CSIT rightfully denoted as maximum of R1, R2, R3. R1, R2, R3, which is the second case. R2 is the highest of them, it comes out to be 63.165 kbps. So the option 4 is the correct one. Let us move to the question. The data is again drawn from question 5. However, we are interested in optimum power allocation. Each SNR state of channel distribution given above. Correct? But this I1, 2, 3 refers to the channel distribution at different time instant. So basically the optimal power allocation strategy is somewhat like that. Now for different channel condition, let us consider we are interested at this this is called water filling, because there is a fixed height called 1 by 1 over gamma naught which we are interested to find, and there are some channel okay, so let me remove this. The concept is as follows: these heights corresponds to 1 minus gamma 3, this side corresponds to 1 over gamma 2, this side corresponds to 1 over gamma 3. The concept is, sorry, gamma 1 it should be. So I consider 3 channel distributions, and you can see that the idea is as follows, that for those channel, this is actually, this height is 1 over gamma 3, so therefore for this one gamma 3 is the highest, gamma 3 is the highest, so this is the strongest SNR. So this one is the strongest channel, and for this gamma 1 is very less, that's why 1 over gamma 1 is high. So therefore this weakest channel, and optimal power allocation or water filling algorithm looks for a particular height set. We have 1 over gamma naught, and we assign power to only those channel where 1 over gammas are less than 1 over gamma naught. So power allocation happens for only these two channel, because these two heights are below 1 over gamma naught, and for those channel whose 1 over gamma is higher than this 1 over gamma naught, there is no power allocation. So optimal power allocation actually assign more power to strongest channel compared to weaker channel, and whatever power allocated is actually this gap between this height 1 over gamma naught minus 1 over gamma 3. This is the power allocated to the channels. So with that we refer to one of the this P over gamma I bar P bar. We first break down what the expression is. So P over gamma I is the power allocated to channel with SNR gamma I, and P bar is the average power. And from lecture, Professor David has elaborately discussed the optimal power allocation, and in this derivation average power constant plays a very key role, which is the summation of this power assigned to gamma I normalized by average power, and the weights are probability of instantaneous SINRs. This is equal to 1. Actually it's upper bounded by 1, but since we are looking for optimal power allocation, we should have this equation equality in place. And as we have seen, it is about 3 instantaneous SNRs are possible, namely 0.4, 6 and 12. We are the I runs from 1 to 3. And by the way, this term, this is a crucial term, P of gamma I P bar. This corresponds to the, as we mentioned here, power allocated to channel with SNR gamma I. This is actually given by this sum 1 over gamma naught optimal value minus 1 over gamma I plus, which means nothing but if it only assign power of this quantity 1 minus gamma naught minus 1 over gamma I if gamma I is greater than gamma naught, otherwise it assign no power. It can be written in this way also. That's this is 1 minus gamma naught minus 1 over gamma I for gamma I greater than gamma naught, power allocated, and if gamma I is less than this gamma naught value, then no power is allocated. Now how do you find the optimal power allocation? Since there are 3 instantaneous SNR only, we can assume that first that all channel have been assigned the power, correct? Case 1, we assume all channel to be assigned power, that is P of gamma i's are greater than 0. This implies, from this equation you can see that gamma naught, this optimal gamma naught which we are about to found, it is less than gamma 1, gamma 2 and gamma 3, correct? Therefore from this equation 1 you replace this normalized power constant by this expression, summation of I 1 minus gamma naught minus 1 minus gamma I times P of gamma I is equal to 1. Let us introduce a slide here. So what we have, so basically we have 1 minus gamma naught minus 1 minus gamma 1 times P of gamma 1 plus 1 by gamma naught minus 1 minus gamma 2 times P times gamma 2 plus 1 by gamma naught minus 1 by gamma 3 times P times gamma 3 is equal to 1. So you can put the values inside. 1 minus gamma naught, it's summation of P naught gamma 1 plus gamma 2 plus P gamma 3. This should result into 1, and I can write it here also, but I'm just breaking it down for your better understanding. This is nothing but the probability distribution. This summation should go to 1, and on the other hand you have 1 over gamma 1. Let me replace the value here. Okay, we can write we can replace value anytime. P times gamma 1 plus 1 over gamma 2 times P times gamma 2 plus 1 over gamma 3 P times gamma 3. This comes out to be 1 over 0.4 into 0.25 plus 1 over 6 into 0.35 plus 1 over 12 into 0.4, correct? And it comes out to be, let me calculate it, 0.25 times 1 over 0.04 plus 0.35 over 6 is 0.4 over 12. It comes out to be 0.5825. Now please look into our assumption here that gamma naught is less than gamma 1, gamma 2 and gamma 3. So gamma naught assumption, gamma naught less than gamma 1. Let us consider the gamma 1 case, because gamma 1 is the lowest of instantaneous SNR. So if gamma naught is less than gamma 1, so it's similar to write that gamma naught is less than all of the instantaneous SNR. So this is our assumption, we started this, but gamma naught comes out to be 0.5, sorry, 0.5825. Can we write the, can we see gamma 1 value is 0.4? Is this happening? No, this is contradictory results. So our assumption of non-zero power allocation to all channels R is wrong. Correct? We assume that non-zero power is allocated to every channel, but it comes out to be wrong because we started with the assumption, and whatever result we are obtaining, the optimal gamma naught value, our result contradicts with the assumption, therefore it's wrong. So let us move to our second assumption, that is case 2, which of course we remove gamma 1 from the picture. That is, we assume no power is allocated to gamma 1, which is P of gamma 1 is equal to 0. Therefore, what we have from the equation 1, P of gamma 1 will be out of picture. The summation will start from I is equal to 2 to 3, 1 over gamma naught minus 1 over gamma I times P gamma I is equal to 1. We obtain from this 1 over gamma naught times P of gamma 2 plus P of gamma 3, and 1 over gamma 2 times P of gamma 2 plus 1 over gamma 3 P of gamma 3. So this turns out to be 1 over gamma naught times 0.75. They are obtaining 1 over 6 times 0.35 and 1 over 12 times 0.4. From this we obtain gamma naught value as 1 over 6 times 0.35 plus 1 over 12 times 0.4 divided by 0.75. Okay, we get 0.687. Now with this assumption we can see that our previous assumption was what? P of gamma 1, gamma naught is greater than gamma 1, but gamma naught is less than gamma 2 and gamma 3. That is how non-zero power allocation is happening for these two channels. And this gamma naught value we obtain from here, 0.686, is indeed less than gamma 2 6 and gamma 3 12. So therefore assumption is correct. We found our optimal gamma naught value, assuming non-zero power is allocated to second and third, like the best and second best channel stream. Correct? So let us add a slide to find what is the power allocated to the stream. Okay. Okay, you have find the gamma naught value to be 0.687, correct? So power allocation for, by the way, you see that gamma naught value is greater than gamma 1, which is 0.4. Therefore no power allocated to gamma 1, which is in line with our assumption. In second case, power allocation for first channel, therefore your P gamma 1 itself, power allocated to gamma 1 is 0. We have already seen, because of this reason gamma 1 is being less than gamma naught. Now the power allocated to second channel, which is denoted by this quantity P of gamma 2. By the way, this is capital P. This is power assigned to gamma 2. This is average power. This is given as 1 over gamma naught minus 1 over gamma 2, which is 0.687 minus 1 over 6. It comes out to be 1 over 0.687 minus 1 over 6, that is 0.16. Comes out to be 1.2889. Similarly, power allocation for third channel, this is the best channel with highest instantaneous SNR. We obtain this as the power allocated to third channel, or the channel with SNR gamma 3 is given as this 1 over 0.687 minus 1 over 12, and the result is 0.087 minus 1 over 12, it's 0.0883, comes out to 1.3722. Power assigned to channels in order of gamma 1, gamma 2, gamma 3 is given as 0, 1.2889, 1.3722. Let us check which of the answers matches. Okay, the first one is the correct answer. We assign 0 power to first stream, channel with the worst SNR, 1.2889 to the second best channel, and the best channel we assign 1.37 optimal power. So you can see the water filling algorithm or optimal power allocation tend to assign higher power to the channel with a stronger SNR. So with that, I end today's session. We'll meet on next Tuesday regarding problems from lectures of week 9. Thank you all.